about 2 meters and nitrogen's about 8 meters as well. Just pick a number, put it in, start the simulation, come back a year later. Anyway, one of these days actually, so I did do my PhD at Caltech on simulation. It is possible to run a simulation like this more quickly, but I would need a supercomputer. It turns out I'm limited by loading and unloading tens of terabytes of data from spinning platter storage, which is 250 megabytes a second.
So how can we download this image?
You can go to my X account, or you can go onto my blog, and I talk about terraforming there, and there's a link to it. It's just a Google Drive.
It's on your blog.
Is it started
Yeah,
or
yeah.
is it finished?
It's old school. Yes.
Okay, cool. I like old school.
Okay.
Oh,
Okay.
actually, yes. This I thought was a hurricane.
No, that's Olympus Mons, and actually you can see here there's let's just say a discretization glitch, which I did not correct because it's fun. Okay.
Yeah,
We're ready to
now
start.
it's exactly 3:30 and you should start.
I will start. Okay, thanks, Tim. For reference, this is my son Yosemite. Feel free to take photos of the presentation, but if you're going to post a photo online, you can obscure his face, I'm pretty good. Okay, cool. Powering the Mars Base, Energy Challenges, Sustainable Settlement. My name is Casey Handmer. I'm the founder and CEO of Terraform Industries. These days, we're making cheap synthetic natural gas from sunlight and air, and yes, Kevin, it's a huge pain in the ass thermodynamically, and yes, it's also very difficult to do it economically relevantly. We're going to move on. Okay, so just kind of, this talk is an exercise in a thought experiment. The thought experiment is, let's say we have 10,000 people on Mars. What now? Okay, so first of all, we have to estimate our power needs, because that's what this talk is about. And here I'm baselining, US baseline is $86,000 per year GDP per capita and 8.4 kilowatts. Antarctica baseline is about $1 million per head to keep people alive there. ISS about $1 billion if you divide the number of people in space by the amount of money we spend on the program. If you look at factory power consumption, it's between 1.3 kilowatts and 350 kilowatts per capita for a person in a factory. So we're trying to get a rough idea for okay, we've got 10,000 people on Mars. How much power do you need on a per capita basis to keep them all alive, to keep their factories operating? Their per capita productivity is going to have to be really high because they have to make lots of machinery to keep them alive, and so on and so forth. So we need radically higher per person productivity, and our putative Mars power budget is, I'm just going to pick 100 kilowatts per capita. So 10,000 people is a gigawatt of total power. Can you wait till the end of the talk? Do you want to sit down? Do you want to watch? Okay.
But I want to ask.
Okay, quickly.
Okay, why did it say parentheses and exclamation point?
Because it's meant to be like, that's a lot of money. Okay, no more questions for the end of the talk. Okay, so we have option A and option B. I mean, people talk about wind turbines and stuff. I'm just going to talk about solar and nuclear. So with solar, we can achieve something like 99% load utilization. That's availability if you use strategic throttling, with about 14 times solar nameplate and 14 times battery at 35 degrees latitude. Same on Earth as Mars because the inclination of the planet is about the same. 14 gigawatts of solar at 100 watts per square meter and 2 kilograms per square meter, which is about Starlink kind of array, is 280,000 tons, which is 2,800 starships. So if you're in sales at SpaceX, you're like, oh. And 14 gigawatt hour battery at 250 watt hours per kilogram. Again, this is nothing spectacular. This is pretty much straight down the middle for current TRL-9 stuff. 56,000 tons, which is 560 starships. Power system totals 3,000 starships, which is about 0.3 starships per person on Mars. You have 10,000 people on Mars. For every 3 people, you need 1 starship just to bring the power system. Your cost is $14 billion for your solar, $14 billion for your battery, and $336 billion, which is assuming $1 million per ton launch into low Earth orbit, which is a total of $364 billion, or $36 million per capita. So it's actually cheaper than the International Space Station. It's not saying very much. Okay, this is just the power system, but that actually gives you some vague idea for okay, well, what does the per capita productivity on Mars have to be for this to make sense, right? And the answer there is $86,000 a year GDP. Not going to cut it. We're going to need on the order of $1 million per capita GDP just to be worthwhile. Miracles required. Starship launch marginal cost of $10 million. 9 refuels to trans-Mars injection. So I'm just order of magnitude type stuff here. Nuclear, on the other hand, uptime of 82 to 84% utilization. That's for US reactors average. So we need 1.2 gigawatts of total power. Nuclear reactors are heat engines and require a heat sink roughly equal in size and weight to the solar array. So 40% efficiency implies 1.8 gigawatt thermal disposal at 300 Kelvin. So again, you can talk about very exotic high temperature reactors. I'm just using boiling water because if it's good enough for Rickover, it's good enough for me. And that's a 3.9 million square meter radiator, shaded, shielded, ideal, 7,800 tons. That's very optimistic. Anyone who's looked into actual radiators on an actual Mars is like, I would like to get some of those, please. So if you build a fully integrated small modular reactor into a Starship, we're limited to about 2 megawatts of electrical power. It's only about 600 SMRs total. 2 megawatts is roughly where SMRs are landing these days. Development cost, maybe 500 million private. I'm sure Kevin can do it for us for maybe 400 million. Development time, 10 years. Of course, if you get the government involved, we just know with nuclear it's going to take forever, unfortunately. Marginal unit cost is 250 million. This is baselined on a submarine power plant. Okay, so submarine power plant is a little bit more complicated than one that goes on the surface of the Earth, but probably less complicated than one that has to fly to Mars. Cost is $60 billion, that's for your launch, plus 150 billion for your reactors, so it's a little bit cheaper if you're doing it in God mode, development mode, and potentially far more expensive. Lead time, so in this case the reactor rather than Starship's on the critical path, because probably even if you started today it would take longer to develop the reactor than it would complete the Starship to this level of miracles. And then you also need to actually build a Mars radionuclear reactor. Oh, and I say a 2 megawatt limit per Starship. There might be another way, but you're not going to like it. That's foreshadowing. Okay, so here's some SMRs. This is Ward Zero down at Valor Atomics, which is just down the road from here. This is the submarine propulsion reactor 1 in Idaho National Laboratory, which was Rickover's first submarine reactor. Pretty extraordinary. Took them less than 3.5 years from like, okay, here's your unlimited budget to launch of the Nautilus. So that's a high water mark for those of you who are like, it's too hard in 2025. They did it in 1950 something, 55. Slide rules, okay. And then this is Radiance reactor, which is also similar size. Also, some SpaceX refugees founded that. So you kind of get the idea around like, they might be thinking about putting this on a Starship someday. Okay, so just to summarize, I have this chart here to show if you wanted to use solar today, these are kind of your range of costs. Your costs come down over time because Starship gets more efficient, or maybe you can make some of the mass locally. And this is your cost for nuclear. So you start today, in 10 years' time, you're ready to go, and your cost could be arbitrarily high, depending on, if the government's involved, it's going to take you longer and cost more probably. I mean, there are people in the government who do good work, but anyway. Okay, what have we got here? There's a fundamental obstacle to Mars settlement. Solar offers distinct advantages in that it's scalable. You can just kind of add another one pretty easily. It's relatively simple. Eventually you could make it locally, although we had a great talk earlier in the session about making a nuclear reactor on Mars locally. I totally approve of that. That'd be great. Heat dissipation is a critical challenge, and the nuclear development introduces major additional uncertainty, but it also requires substantial engineering chops. So one of the major problems that SpaceX still faces in its like post-economic scarcity regime, like basically Elon can now raise arbitrary amounts of money, is they don't have arbitrary amounts of engineering talent, and they have to fire hose that talent at the remaining problems with Starship, so they don't have like infinite talent to do reactors at this point. Okay. Hold on. So I was like, okay, well, SpaceX wants to drop, like Fleury-Montes is probably their leading candidate for a landing site, which is 35 or 34 degrees north, similar latitude to Los Angeles actually. What is the solar power situation there? Obviously for nuclear it doesn't matter that much, but for solar it does. So this is your latitude, and this is your seasonal effects of solar. So on this axis we've got latitude, and on this axis we've got days of the year. On Mars there's about 660 days in a year. And what we see is that, and then the numbers are average irradiance in watts per square meter over the course of a full day. So if you need batteries to power at nighttime, but in solar 180, you're getting 180 watts per square meter irradiance at 34 degrees north. What you see is you get plenty of power pretty much all the way through the year, and then you get the northern winter, and it's pretty grim for about 2 months. Well, two Earth months, that's 60 days or so. Okay. And actually, if you were to put the base a little further south, you kind of avoid that problem. But the problem then is your solar irradiance is high all year long, you're warm all year long, all the water that was in the ground long ago has since departed to more northern climes where it's colder throughout the year and there's maybe less ice, which is a major problem. Okay. Oh, and then this is just a photo of Fleury-Montes on the bottom right. Okay, but because I like to overcomplicate things, I thought let's add dust and clouds, and so I yanked some data out of these papers by, this is before LLMs, basically copying these pictures and then color matching the color bar. And so I started off with this chart, and I ended up with this chart. So just to be clear here, we're talking, this is ground mount solar. So this is my favorite kind of solar, where you just put the solar panel on the ground and walk away, like in The Martian. And this is incorporating dust and cloud. And what we see here is that actually the color bar has changed. So we're getting this saturation point in the bottom right, where there's a couple of very, very hot months in the summer in the south, but the rest is pretty miserable. And then here we're kind of seeing pretty uniform all year round, except for that kind of 2-month quiet period in winter. This is, if you're tilting the solar panels towards the equator, gets you a little bit more power. This is one-axis trackers. So most solar arrays that are installed right now in the United States are on what's called single-axis trackers. So these are essentially rotational beams that run north-south, and then the modules can tilt down towards the horizon for dawn and dusk, but less so in the middle of the day, which actually helps them because of the way that humans use power. But actually this tends to accentuate the difficulty in winter because the sun is low on the horizon, and it never really gets overhead, if that makes sense. And this is 2-axis trackers, so if you want to go splurge completely on modules that can track the sun with 2 axes, and I know Kevin spent a lot of his time working on that too. It's a real puzzle, but at least you get relatively uniform power levels all year long. You get about 200-ish rather than 160. I don't think it's worth it, but yeah, opinions can vary. These are the numbers. Okay, so that's it for solar for now. And we've got some time, so I said you weren't going to like it. If I'm prepared to spend infinite time and money, is 2 megawatts per Starship really the best I can do? The answer is no. Now, I just want to preface this by saying, if you find a huge body of pure water ice that you can put a rod well in and you can dump heat into it and get cold coolant back out, this doesn't apply. And if you have an enormous HAB and you're putting a nuclear reactor inside the HAB, like we do with submarines, and you can use that HAB as your heat dissipation, then this doesn't apply. But if you're landing a Starship on Mars and it has a giant power outlet, like the ones you see on the wall here, but much larger on the side, and that's your only constraint, I just want to press a button and it starts making power. What's the most power I can get out? It turns out that you can combine a jet engine, which is an open Brayton cycle engine, so you've got a series of compressors here. Ignore the fan. You've got a series of compressors, and then you've got some combustors, and then you've got your turbines, which turn the engine. You can put an electrical generator on that and sell it to OpenAI for roughly 10x markup right now. But you can replace the combustors with a Nova core, which these are available in Nevada. You just have to know where. And you end up with something like this. There's a little bit of a puzzle around this because Mars's atmosphere is so thin that it's actually very hard to efficiently or compress it efficiently enough to make this cycle work. But it turns out that whereas in a latest generation jet engine on an aircraft, you might have a 40-to-1 compression ratio. So in the combustion chamber, it might be on the order of 10 or 12 Earth atmospheres, because they're operating in the stratosphere. In this case, it'll actually be in the reactor core just under 1 Earth atmosphere, which is almost a 80x compression ratio versus Mars ambient. So I have this giant Couette inlet compressor, because I'm not very talented with CAD. So this does your first stage compression. You've got a second stage axial compressor, reactor core, and then a big expansion turbine that blows the air through. So like our talk earlier this morning, the emphasis is using some of the power to move huge volumes of Mars air through, which then in turn allows you to cool, provide this cooling stage, and you're no longer constrained by having to spend most of your mass budget shipping radiators all the way to Mars just to be like, I got a cooling leak. So this is a fun one. I kind of hate it. Just to be honest, to be clear, this is your 9-meter diameter Starship. So this just sits on the top, it lands, plug and pray. 1 second at the end of the talk, thank you. So we have no damn radiators, $50 billion development cost. I'll do it for you for 49. There's one challenge here actually. If you get carbon dioxide really hot, you start to get dissociation. So it starts to form carbon monoxide oxygen pair. And in those cases, actually, it turns out the carbon monoxide is more corrosive of the two. So your Nova core had a graphite core, and that would, it's made of pure carbon. So you've got carbon dioxide, carbon monoxide, oxygen, and pure carbon. It's going to dissolve like a sugar cube in hot coffee. It's just going to disappear. So almost instantaneously. So you're going to have to do a little bit of engineering on your Nova core so it's resistant to those extremely high temperatures. And yes, you could also have a heat exchanger and a secondary exchange, so you're running more air through it, more ambient air through at lower temperatures, or you're not trying to put the core, the radioactive core, the neutron resistant materials that also have to be carbon monoxide resistant. Details. But it could be done. Okay. Is it really important? Are you bursting? Okay, sure.
Okay. If you attach to this to the back of a starship, it would shoot gases out the back at very high speed after they're done turning the turbine, and you could use that to blast the rockets.
It's true, actually. You could use this Nova core to help you get to Mars faster. Okay, bonus round. Good suggestion. Bonus round, surface synthetic fuel choice. So So it's a whole new world on Mars. We don't have to be stuck with like gasoline. We could do something new. What could we do? There's so many choices. We need fuel probably. This is something in the case of Mars. We need fuel for suits, for rovers, for remote outposts, for generators. Whole new choices. And pull out your phones and hit that QR code because this is too small to see, and I know that. But what I've got here is, I don't know, roughly 40 different fuels and oxidizers. I've got class of fuel, chemical formula, density at SLC, density as liquid, energy density, oxidizer of choice, oxidizer ratio, enthalpy of combustion, energy density, importation mass, which only matters for batteries, melting point on Mars, boiling point on Mars, melting point in the HAP, boiling point in the HAP, viscosity, vapor pressure, synthesis complexity, synthesis efficiency, and toxicity. These are all very important things, right? Because the last thing you want is a fuel where you have it sitting in your rover and then you take it outside and it freezes and you can't pour it anymore, right? Or you have a fuel that's liquid outside, you bring it into your rover and it boils off and asphyxiates you. Or it suddenly turns your rover into a bomb because your rover is full of oxygen that you need to breathe, right? Or it's a beautiful chemical and it's liquid at both ambient temperatures inside your rover and also outside on the surface, but its viscosity is like 100 times higher than honey. So you're trying to pour this pourable fuel, but it takes 5 hours. Or it's a beautiful fuel, but its synthesis complexity makes fish and chops look like a walk in the park, for example. So just mind-boggling stuff. Okay, if you look across here, we see a green kind of area here, a green area here, and a green area here. And I know you're desperate to know what these chemicals are. So I'm going to blow it up for you. I'm going to show you. This one's paraffin. Okay, so paraffin has this nice feature that it's waxy and it's solid, so you don't have to worry about vapor pressure. It's relatively stable. Technically, it's ingestible. Ask me how I know. We have magnesium. Magnesium has a really neat trick, which is that you can burn it in carbon dioxide, which means you don't have to bring the oxidizer. And even burning with carbon dioxide, the energy density is acceptable, right? It's actually comparable to gasoline. The disadvantage is that the exhaust is solid, so you're talking like steam train kind of thing with the ashes like falling out the bottom of the track. And ammonium chloride, nothing bad associated with this chemical has ever happened ever. I'm sure it's completely okay that we'll just extrude this with a plasticizer into like long threads like a 3D printer, run it through an FDM nozzle, and burn it in a combustion chamber. Nothing will ever go wrong. Definitely do not Google that explosion that happened in Las Vegas in the 1990s. Okay, so my conclusion here is that this will be our fuel of choice on Mars. But I am open to questions and suggestions and refutations and offers to duel at dawn.
This code is almost uncrackable.
Okay, yes sir.
Question about the expected mass of your reactor. I mean, you mentioned Rickover a couple of times. I understand on those submarines, we're talking about roughly 10 tons per megawatt generated
Yep.
for your nuclear power plant.
Yep.
Now, you said in certain circumstances on Mars, you might need more mass for heat dissipation.
Radiators, yeah.
On the other hand, this is 50-year-old technology, so I don't know if today there are
Yeah.
more efficient per
Yeah, there are.
weight generators out there. If you can talk a little bit about what the options are, since transportation costs are important.
Yes,
in
absolutely.
Getting the most efficient megawatts per ton kind of unit up to Mars.
Yeah, so for Starship you have a volume constraint and a mass constraint. It is possible to push the core temperature up, but it's a kind of an exponential cost penalty for doing that. And there's roughly a quartic mass benefit in terms of the temperature of your radiator for doing that. So I don't know, there's kind of a trade-off to be had there. Yeah, I think it's hard to engineer something to be heavier than it would need to be in a submarine, that's for sure. But at the same time, the submarine is surrounded by an infinite amount of water at 300 Kelvin, so it's not a problem.
I would even argue that it's never been the design optimization to try and make nuclear reactors like. It's always been.
There've been plenty of study like paper reactors for like say 400 is an example. NASA's tried to do for space applications. It's a real pickle, right? So Jared Isaacman has made no secret of the fact that he wants NASA to go and figure out nuclear electric propulsion. If you've got good ideas on this front, let him know, because I can't make the math work in my head, right? Its solar sail seems to do more thrust for the same mass and much less money. Yes, sir.
Was it the magnesium fuel that had a solid byproduct?
Yes.
Would that,
Magnesium oxide is a ash.
would that byproduct be useful in construction of other roads and lane?
Yeah, possibly, but the problem is like if you're running a turbine or something, you just end up with this material sintering onto the inside of your turbine blades and they don't work anymore. Or an internal combustion engine doesn't work with that. Fuel cells, you can't eject it out with a liquid, so it's a bit of a puzzle. But yeah, for making a solid rocket fuel or something, it's fine. But this also works for that. Yes, sir.
Yeah. So you used U.S. GDP per capita as part of this kind of power estimate benchmark.
Yeah.
Although only a small portion of the U.S. population actually works in manufacturing, and
That's true.
most of the industries that bring in most of the GDP are things like finance, which, you know, theoretically make things
yes.
more efficient,
Yeah.
but in practice,
Yeah,
we may not need so much.
Basically, what I was trying to get at there, and actually my talk that I gave in 2018, like 3 weeks before this guy was born, gets at this in more detail, is that we're going to need radically higher per capita productivity on Mars. You measure productivity with GDP. Obviously on Mars you might have a smaller Wall Street and a larger manufacturing sector, but that sort of productivity is going to require radically more power. So like that was to motivate 100 kilowatts per person, but no one here stood up and said, that's ridiculous, so I think I might have oversold it. Okay.
Okay, also,
yes.
another issue with the giant nuclear jet engine, dust.
Yeah, I mean, that could be a problem. So actually, the nice thing about the axial compressors is that you can centrifuge some of that stuff out.
Oh, okay.
And also, of course, you're going to be irradiating carbon dioxide that then spews out onto the surface of a planet that's also exposed to radiation from space, so I don't care about that too much. But, yeah.
Not if you use a heat exchanger.
Sorry?
Not if you use a heat exchanger.
No, yeah, not if you do. Yes.
Yes, just going back to the point you made about locally producing things so that you don't have to have a high transport cost,
Yeah.
and specifically on solar.
Solar, yeah.
The Mars soil has all the ingredients needed to create glass, no?
Yeah.
Silica and...
I mean, it's more or less undifferentiated basaltic melt. So like there's everything you possibly want is there. All you need is a way of converting that into raw
So
materials.
can't
which
you
is not
just
trivial.
get the transport the machinery first and just have an infinite number of
Yeah,
solar panels being produced there?
in theory, but if it was so easy, why can't I do that right now here in Nevada? Like, it turns out that making solar panels is slightly non-trivial. Yeah, but actually, like Blue Origin has demonstrated that they can turn a lunar regolith simulant into photovoltaic panels. The question is, what is your like energy return on investment, right? So if you're going to spend $10 billion putting this factory on Mars, how quickly does it produce as much power as $10 billion worth of solar arrays that you just deliver from Earth would have done? And SpaceX's overall goal is to make shipping stuff so cheap that actually you probably just want to ship stuff from Earth in general if you can. But we'll see. Yes, sorry. I'm going to call a nepotism here. After the talk, thank you. Next question. Yes, on the back.
So I maybe wasn't following, but I thought you said you could compress the Martian air,
Yeah.
and then if you have a denser pile of air, it would be better cooling.
So the Brayton cycle is how jet engines work. Suck, squeeze, bang, blow. The compression is an essential step in extracting power from combustion, or in this case, nuclear heat. Yeah, so the compression is an essential step in that thermodynamic cycle.
But what I didn't understand was when you compress the air, it's going to get hot.
Yes.
And my understanding was you're trying to use the air to cool your like.
Yeah, so it's true actually. Yeah, so one of the advantages of the Nova core is it's really damn hot.
So it's so hot that even if you compress the air.
Yeah, it's like 1100 Kelvin or something. It's
So it's still more efficient to transfer and compress hot air than it is with Brayton.
well, that's the main reason you can't compress to 40 atmospheres, right? Because then it gets too hot. Or unless you have an intercooler, but I don't really want to do that.
But I think the bottom line is you're saying it's better to compress the air even though it heats it up.
You have to. So in the thermodynamic cycle, the Brayton thermodynamic cycle, it's the same as in a car. You have to compress the gas in order to get work out of it when you expand it.
Okay.
Yeah. Or say you get much more work. You get much more work out of it by compressing and expanding than you would by not compressing. In fact, the major design goal of these advanced turbofan engines is to increase the compression ratio in the combustion chamber because that allows higher fuel efficiency. And that's one of the reasons that the rotating detonation engine is potentially more efficient because it has a much higher compression in that detonation front. Much harder to run, obviously. Sorry. Yeah, it's a good question. I'd say like
I think I understand.
look up Brayton cycle and then yeah. Okay. Yes, sir.
So if I understand the premise of your scenario here, you're saying somehow we got 1,000 people on Mars and never built any power generation at all, so it's
Well,
not an
10,000.
incremental growth.
No, you have to
You're
incremental
trying
growth,
now-
but it's like the question is like, okay, now we're at 10,000 people. How do we get here? You know, did we have to send a third of a starship per person in order to instantiate their energy supply, et cetera, et cetera. So it's kind of saying, you know, if we imagine we've got this nice AI generated, okay, 10,000 people would be a larger dome than that, but like this is the world we're in. okay, now we go on our school field trip to the power plant. What must it look like in order for this to be possible, right? And what I'm trying to say is, I feel like, you know, at these conventions and stuff, it's great. We hear lots of different ideas about all kinds of things, like farming and all that kind of stuff. But I really like to drill into like the nuts and bolts of the infrastructure. Like, how are we actually getting the power that we need? Because if you don't have quote unquote infinite power, a lot of other things become much, much more difficult, right? You do not want to be constrained by power. You don't want to be constrained by water. You don't want to be constrained by land, mass. You really want to be constrained only by labor, right? You never want to be spending labor to solve some other kind of scarcity, some other constraint. Yes, sir?
You mentioned something like 8.9 kilowatts per person, basically per capita per person. Where did you come up with that figure?
I basically did 100 here. I just made up 100. Yeah. So 8.4 is United States, but we're pretty energy rich in the United States.
Yeah. But I'm trying to say are you taking into account like the energy that we drive with the car, the energy we use at home, thermal energy in the hot water heater? Or what is I think that's not just pure electricity.
No, it's everything. Yeah, and roughly 2/3 of energy consumption in the United States is chemical energy. Roughly 1/3 is electricity, and about just under 1% is food. But you know, obviously, the chemicals that we need on Earth for making plastics, we have to make on Mars as well, and that's inherently inefficient interconversion process. So you know, the answer is like we'll probably need more than 100 kilowatts, right? Just to be perfectly blunt. Like at the end of the day, you want to have a relatively small number of humans with a very high per capita allocation of robots and machinery building things, so that they don't have to sit there putting in screws themselves, right? If you think like, how many people do you need and how productive do they have to be to achieve closure, like economic closure in an almost autarkic, self-sufficient system? It's mind-boggling. It's absolutely astounding. You could just imagine, okay, Iceland's 350,000 people, and we blockade Iceland because we don't like them. How long until they regress back to the Middle Ages of like quality of life, which we know can sustain indefinitely in Iceland? On Mars, obviously, you would not like regress to the Middle Ages, you'd regress to like almost instant death. And the answer on Iceland is like 3 months. Right? And say, okay, well, we're going to give you 10 years advance warning. We're going to blockade you. You can import anything you want on one very large container ship, which is about 2,000 starships worth of stuff. Now how long can you last? And that's a very, very hard problem to solve. But it's way easier than solving it on Mars. Yes, sir?
Might be crazy and overly simplistic,
Good.
but can we not buy a used nuclear reactor from a submarine that they're decommissioning, put it in a starship and send it to Mars as the initial power plant that gives you power to do all the other things you need to do?
It's an idea. The major challenge there is heat disposal, right? How do you get the heat out of it? In a submarine, it's not a problem. On Mars, it is. And then naval reactors are, I think, significantly heavier than Starship capacity.
1,650 tons for an Los Angeles class.
1,650?
Yeah.
Yeah, so that's an interesting puzzle for you all.
So you need
A submarine is about 2/3 reactor, right, in terms of the engine compartment. Obviously, the reactor core itself is somewhat smaller. Like, that seems really large for a boat. Why is it so large? And then you hear the name fast attack submarine. Like, how fast? Okay. Yes, sir?
It seems like also it's kind of radioactive, right? Used ones are a lot more radioactive.
Yeah, but like Starbase is pretty remote. It's probably fine.
They're like 9,000 yards from your city, 6,000 yards from Mexico.
Okay, but like if it turned out that like technically it was 100 times better to launch a reused nuclear submarine power plant than to build a new one from scratch, we can adjust the paperwork. Okay.
You don't think that's true?
No, I don't. Yes, sir.
I got to address this because it's similar to the question I was asked. It's really similar. I mean, designing a nuclear reactor using computers where you simulate it and you do it in CAD, that is not the hard or expensive part of a nuclear reactor. That's the easy part. Trying to retrofit one that was designed for a different purpose is much harder because you're dealing with all these things that are just not related to the design that you want to have.
Actually, there's a lesson in that. The amount of money that NASA has spent trying to fit, the proverbial 20 pounds of whatever into a 10-pound bag is absolutely mind-boggling, right? If you say, well, how much did the International Space Station cost? $400 billion. And why did they build it, with the 43 flights over 30 years? Because it's modular to save money, right? They could have just recommissioned the Saturn V. Even if it cost $50 billion to recommission the Saturn V, they could have launched the entire International Space Station in 2 flights. All right, in terms of volume. Okay, 3 flights. It depends if you mass or volumetric area inside. Right, or a single Starship has twice the internal volume of the entire space station. Right, and the entire Starship did not take $400 billion in 35 years to develop. Right, you want to develop key things. He's dying. He's dying. Okay. Well, I didn't see any. Feel free to grab this URL, and I welcome feedback. Okay, I'm not that hard to find online. My email address and so on. We're hiring, by the way. But if you have feedback, you want to add something to this, just let me know. There's all kinds of crazy ideas there. Actually, Zubin the other day suggested using the perchlorates on the surface of Mars as your oxidizer. So you could have your solid, edible paraffin fuel, and then you just shovel a bunch of perchlorate off the surface, and that becomes your oxidizer. And that also has a solid waste product, salt, obviously, but you can decompose it and then toss the salt. Okay, thanks, Tim. Thank you.